All right, so I'm here to talk a little bit about LLVM optimization. We often kind of get caught up in some of, in my opinion, the more fun and interesting stuff that's going on with LLVM these days. There's a lot of things going on. We have things like Sanitizers, we have Clang, we have lots of interesting use cases for LLVM. But I think it's important to not lose sight of kind of the original use case for LLVM, which was an optimization framework. And in particular, I think that it's a little bit useful to give some context to the current problems and successes that we're having using LLVM to optimize modern code. And when I'm talking about LLVM for optimization, I'm mostly talking about optimizing modern C++ code. I'm not really talking about some of the more domain-specific uses of LLVM, which are really, really interesting, but are very different. They're not as accurately reflected by this talk. So the first thing I want to do is kind of give a little bit of a brief overview of kind of the state of optimization in LLVM today. So there's some things that LLVM is doing pretty well at. I'm actually pretty pleased with these things, right? We're doing a really good job of kind of scalar simplification and general recombination of programs. And this is something that LLVM has historically been an excellent tool for doing. A lot of people have probably seen the inst combine monstrosity that is in LLVM. It can be very hard to understand, but it's incredibly effective. We're also pretty good at loop simplification and actually removal. LLVM does a remarkably good job of understanding and being able to compute across loops. And I want to be very clear, this isn't the same thing as transforming loops, right? That's a different thing entirely. We're also really good at kind of idiom recognition. We have lots of cool stuff we can do there. And doing kind of inlining and abstraction decomposition, right? Kind of breaking down large and complex programs into increasingly simple programs that are easy to understand, easy to optimize. But there's some things that LLVM is struggling with as well. There are two things in particular that I'm calling out here. I'm not trying to say that there are only two things that are bad with LLVM, but there are two things that I think are kind of notably missing in the LLVM optimization framework. One of those are loop transformations, and these are the more advanced kind of loop slicing, loop peeling, loop unswitching, loop switching, loop fusion. There's a whole suite of loop optimization that LLVM doesn't really do. It doesn't even try to do right now. And this is kind of a missing thing. If you care about your loops actually getting laid out in exactly the right way for a microarchitecture, LLVM is going to struggle to do that with a lot of loops today, and that's kind of a missing feature. There's also a big missing feature that's actually very near and dear to my heart, profile-guided optimization. And I'm going to talk a little bit about that later, and there's going to be a lot more talk about profile-guided optimization here at this conference. But then there's the part of LLVM that makes me really grumpy. And these are the ugly things in LLVM. LLVM isn't bad at any of these things. All right? These are things that it should be really good at, and it just isn't right now. Okay? And so I consider these kind of the ugly warts on LLVM that we need to go out and kind of clean up. My number one grief is that there is no analysis information in the LLVM inliner. This kills me. We have an amazing suite of analyses over the program in LLVM, and none of them are available to what I consider to be the most fundamental and important optimization pass in the compiler, the inliner. It instead is making decisions in the absence of all of the information that the rest of the compiler has. And this causes some pretty serious problems. We also have a case where there's this selection DAG thing. And there's been a lot of discussion on the mailing list about the selection DAG and whether it's good or bad or what we're doing with it or what we aren't doing with it. And I see the selection DAG as a very fundamental limiting factor of LLVM. It puts an absolute cap on the number of things we can do when we get a particular program pattern out of the middle end and we try and realize the correct architectural implementation of it. If any part of what comes out of the middle end crosses a basic block boundary, we lose. We give up, we go home, and that's unacceptable, right? And this isn't a limitation that has to be there. It's just an artifact of the current architecture we have. And this is something we need to kind of clean up, we need to fix. And I'm really, really excited to see pieces of this start moving forward and to see us start really understanding how to move past this basic block boundary limitation. The third thing is LTO, link time optimization. Link time optimization is something that LLVM has kind of promised to do for years. And it's never really delivered as well as it should have. For a long time, people were focused on the problems of link time optimization around scalability. And that was because there were very serious scalability problems in the IR and the way in which we linked together IR modules. We've addressed a lot of that, but we haven't actually gone and looked at how we're doing link time optimization. The path structure we use for link time optimization is insane. It makes absolutely no sense. We optimize each module as if we won't be able to do link time optimization, and then later we go back and try to, just optimize it again. It'll work out fine. Right? And so these are kind of warts that have built up over the years in LLVM, and this is stuff that we really have to go in and clean up and fix. So at this point, I would really like to kind of put some numbers, to put a finer point on exactly where LLVM is doing. Because when you look at these three things, right, you look at some of the things we do well, some of the things we don't do at all, and some of the things that we should be doing well, but we actually kind of have pretty big problematic bugs in. It's easy to get the idea that LLVM isn't doing a very good job at optimizing your code. And I don't think that's true. So I've got some numbers, and these numbers, I have this really horrible slide here. There's some fine print for these numbers. So the fine print goes like this. First off, I don't know if you guys read Phoronix, but I unfortunately do. And I'm sad every single time they post benchmark numbers. And so I'm going to try and give you as much information about exactly how I got these numbers so that you understand the context and you don't think these numbers are just completely made up. Unfortunately, these are not numbers that you can reproduce yourself, and so I felt especially compelled to give some context even in the slides. So the important things to realize is that, one, the numbers I'm giving are not single benchmarks, right? These are aggregate numbers. I've taken the geometric mean of a number of different benchmarks and kind of pulled it together to give you an overview. I have to do that because some of these benchmarks are internal to Google. They're not public. We can't share them with you guys. I'm going to give you as much information about the nature of the benchmark as I can. And apparently there's an alarm. So the other thing that's really important is that these numbers, I've tried to craft these numbers in a way that I find not confusing, and unfortunately I've failed. There's no good way to represent numbers for a benchmark, I'm afraid. So what we've got is we've got the time it took for LLVM compiled programs to run, and the time it took for a GCC compiled program to run, and we've got the ratio between them, all right? Now, if the actual benchmark was measuring something else like queries per second or megabytes per second, or I don't care what it was measuring, I've converted it around until it's actually measuring a unit of time, just so that we have this very consistent basis. All right? And as a ratio, that means that a smaller ratio is very good for LLVM, and a larger ratio is very good for GCC. And I am primarily comparing against GCC because, frankly, GCC is the best there is for the code that I work with. All right? For the code that I'm dealing with, GCC is simply the best optimizer we've ever thrown at that code. Now, the final thing I do want to mention is exactly which GCC I'm using and which LLVM I'm using. I don't have the specific revision number. I tried to dig it up, and I don't have an exact revision number. But this is several months ago off of trunk of LLVM. There were no special patches applied to LLVM in any way, but it might have missed your favorite optimization if you've committed it recently. The GCC that we're using here is the Google GCC, and so there's actually Google branches of GCC in the open source GCC repository. You can go find the exact copy of GCC. It's got all the same pieces to it. There's nothing secret or unavailable going on here. But it is a particular set of patches on top of GCC that we find help our benchmarks out. And so I've tried to give it the most competitive demonstration of performance I can. I'm really using the best GCC we have against LLVM here. I'm not trying to stack the deck in any way. Okay, so that's the fine print. I just want to make sure we're all on the same page here. So some numbers. So I've got these very generic high-level descriptions here, but I'm going to talk a little bit about it, okay? So the idea is that for servers, right, for big, large server applications, right, these are not small programs, these are huge programs, right? They're serving lots of QPS. We're seeing that GCC has about a 4% advantage over LLVM, all right? On average, that's what we're seeing. And this is very, very consistent, and this has been consistent for a couple of years now. And so this is not something that's actually changing a whole lot. For image processing workloads, and I looked at a bunch of different image processing workloads, right? And they're pretty significant image processing. They're doing different types of image processing and different types of benchmarks here. We're seeing about a 3% advantage. For video codecs, not terribly surprisingly, nothing matters, okay? And this is true for every video codec benchmark we've ever run through it. Anytime we think we've discovered this huge advantage in a video codec when you compile it with either LLVM or GCC, we run the benchmarks a bunch more time, and it turns out it was a fluke. Right? It was a fluke in the hardware, it was a fluke in the machine we ran the benchmark on. We see no real discernible difference here, and this is not surprising because almost every hot path in every video codec I've ever looked at that we care about is written in assembly, and so the compiler had better not make a difference here, okay? All right, so then we get to my favorite numbers because I can actually tell you exactly what pieces of software we're benchmarking, even though I can't share with you the exact benchmark we ran over that software. So we benchmarked 3 particular libraries that we care about a lot. And the reason we care about a lot, just to be clear, is because these high-level, kind of macro-level benchmarks, we find that these are deeply influenced by the performance of these 3 libraries. And so we watch them very carefully. For OpenSSL, there's no difference at all. Again, this should not surprise anyone. This is a reassuring thing. It's no news here. OpenSSL is almost entirely written in inline assembly, right? This is not a big deal here. All right. Protocol buffers, though, are terrifying to me. 12%. GCC is 12% faster than LLVM for protocol buffer generated code. All right? That number, I can't explain it entirely, but it's motivated a lot of work that I've done on the LLVM optimizer, and I think that this is showing a significant weakness in the optimizer. There's also a benchmark called Snappy. You can find Snappy is a compression library that Google open sourced a while back. You can find the source code for this library. This one runs about 5% slower. This one doesn't scare me as much because Snappy, as does any other compression library, it has one hot loop. Right? If you lay that loop out ever so slightly wrong, you get huge swings in performance. It turns out that LLVM lays out a few instructions in that loop wrong. It's very unfortunate, but fixing it is hard to impossible. So that's where we are. GCC gets very lucky here, and by lucky I mean that we've actually hammered on GCC for so long that it's getting it just right. Okay. Questions about the benchmark numbers? I don't want to move on too fast because I know numbers are kind of sparse up here. Yeah. Great question. So the question is, I didn't mention options. The exact same options were used for both compilers. The options used were, what, do you want to argue, Diego?
No, I don't want to, what do you mean exact, sorry. No. Don't you need to use different options to enable the same things in both compilers?
No.
So O2 means the same in both?
Essentially.
Okay.
We're benchmarking O2, so this is -O2 is the optimization level for both GCC and LLVM here. I made very sure that these benchmarks ran after a couple of things that went into LLVM's O2 that are actually in O3 for GCC, got moved into O3 for LLVM.
Right.
So as far as I know, these are relatively comparable kind of optimization strategies. LLVM's binaries are significantly smaller than GCC's binaries at these numbers. By about 5 to 10%, it varies a lot. I didn't put up specific numbers. The most interesting flag is probably this is not tuned for any specific microarchitecture. This is just tuned for x86 64-bit. No microarchitectural tunings. We did run it on a kind of modern Intel system, though. All right, so that's where it is, right? If you look at this, 10% on specific libraries, kind of worrisome. 2 to 4% on large macro level benchmarks. That's the state of the world. That's kind of the world that I look at. And one of the things I would really like to see is I'd like to see these two compilers kind of keep that competition going, because from what I've been seeing, these benchmarks are very flat. They're way too flat. We aren't really driving optimization forward, and so I'm really hoping that as we get both compilers to be competing, we're going to see a lot more developments here. All right. So the one thing I do want to point out is why that 12% difference is there. I'm going to try and explain it here. I'm probably going to fail, but I'm going to try and explain it here. This is a theory. I can't actually prove what I'm about to show you because we haven't written all the optimizations we need to actually benefit and fix the problems. But this is the best theory I have, and I hope it'll at least be enlightening as to how some of the optimization passes in LLVM actually work. This is going to be a bit of a deep dive through some code. Okay. As far as I know, this 12%, this huge regression, and 12% in my world is a massive regression in terms of optimization, like benchmark performance. it's all in the little things. There's no like massive like optimization that is missing from LLVM. That's not what it is. It's a bunch of little things all kind of conspiring to really cripple the performance that we have here. So I want to look at some code. All right, so this is the code I'm going to start with, and you all may be very surprised to see me put this completely useless piece of code on the screen, right? It's pushed back into a vector. The screen is very hard to read, for which I apologize. All I'm doing is pushing like 1, 2, 3, and 4 into a vector, and then I'm throwing it away. And the amazing thing to me is that if you run this code through LLVM in any optimization level you like, it does not delete the code. And I have no idea why LLVM does not delete this code. And the most surprising thing to me is that as far as I can tell, most of the reasons why LLVM doesn't delete this code are the same reasons why LLVM regresses by 10 to 12% on protocol buffer benchmarks. And I found that just really surprising. And so I'm going to try and explain this using a contrived example. But I want you to keep in mind that the same story is actually going to repeat when we look at protocol buffers. The other thing I do want to mention, just as a caveat, in case anyone is like feverishly typing away, this example, it was originally written against a particular version of the standard library. Each version of the standard library I have tried exhibits different behavior in the optimizer, like radically different behavior in the optimizer. And so it's very hard to reproduce the exact set of things that I'm going to show. You'll often see very similar things. You'll see patterns that match the same fundamental root cause, but actually happen in a different piece of code. Okay, so what is actually going on in pushback? This is a contrived pushback implementation. I am simplifying as much as I humanly can out of this code. All we do is a few things. First, we check to see if we've run out of storage. If we've run out of storage, we have to grow our storage. This isn't too surprising. That's how vector works, okay? Once we have enough storage, we go through and we add a new value to the vector. Nothing crazy going on here, right? I mean, I'm skipping over a lot of details. If anyone here has implemented a standard library, I'm sorry I'm not doing your pain and suffering justice here. Okay, but the interesting thing is what's in grow, right? Because I mean, this function's useless. This is a tiny little function. It doesn't matter at all. So grow is the interesting function, and this is vaguely what grow looks like in some STL implementations. Not all of them. They're all different now, but this is an interesting representation of grow, okay? It's pretty straightforward. The first thing we're going to do is we're going to figure out how big we need to grow, right? Vector has a kind of doubling-ish pattern of growth. It also is going to clamp the growth based on a max size, right? Nothing too fancy there. We allocate some memory. I've just written allocate here, all right? Yeah, there's a big hand wave going on there, right? But it means operator new gets called. It means we allocate memory. The kind of expected things happen. All right. So then we go on and we set up some variables, move things over, store the new state. We kill off the old thing. Nothing surprising to me. Is anyone surprised by this code? Anyone want to wager how much IR is required to represent this function? How many people think that less than 50 lines of IR to represent this function? Oh, come on, be honest. I thought it was less than 50 when I first saw this function. Okay, a couple people. How many people think it was less than 100? How many people think it's less than 500? It's way over 100. Way over 100. Okay, so just these first 4 lines of code. Okay, we're just going to look at those first 4 lines of code. And the reason we're just going to look at them is because that doesn't even fit on the screen. I mean, like, you can't read this. I don't know what it's doing, okay? Apparently, pointer arithmetic got hard in the IR. We're doing something very fundamentally wrong when we're generating this much code to grow the size of a pointer, right? The code to allocate is actually just this 4 line down here. That's nothing at all. This isn't like the call to the allocate function. There's no other logic going on here. That giant block at the top is just trying to double the size. That's all it's trying to do. This is after every optimization pass in LLVM was run over it. Before that, it's like 5 or 10 times longer. Okay, so we've done something terribly, terribly wrong already. I've worked on trying to fix this. I don't know how to fix this. This is a mess. But this is what you get. Okay? So when you're thinking about grow, don't think about this lovely little 10-line function. No, 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 no. Think about hundreds and hundreds of LLVM IR instructions. That's what you're actually dealing with here. And then think about what happens when the inliner sees this, right? Because the inliner is going to work bottom up. It's going to start at the very bottom, and it's going to work up. So the inliner, it goes and it says, oh, grow, okay, I can inline grow because there's only one caller. I'll go and inline grow, and so it inlines grow. And then you get, C++ code like this. I didn't put the IR anymore because, well, it wouldn't be very functional. But you can imagine hundreds of lines of IR for this if block now, right? So let's think about what vector does. Let's think about the very fundamental level, what vector does. We now have hundreds of lines of IR for the thing that vector is designed to push into an amortized constant. This code never executes. It cannot be on your profile. Like the algorithmic design of vector says, this isn't in your hot path. Okay? And yet we're inlining hundreds and hundreds of instructions of IR into pushback just to support grow. And this will happen today. If you actually write code similar to this, you can cause this to happen in LLVM today. And it's really infuriating. Because now, when you go back to my simple example, right? When you go back to this simple example, you're going to see that, like, well, we're not going to inline this pushback, even though we have, a 1 there, even though they're constants, even though we actually know what's going to happen. We're not going to inline anything because it's enormous. Right? We have this huge memory allocation thing here. It's not even dead code. Think about it, right? This actually has to allocate memory that one time. And so the inliner gives up, goes home, and all of this code sticks around. Okay? And this is one of the many ways in which code that seems very simple, seems like we should just like delete the code, no problem, actually completely confounds LLVM's optimizer today. Make sense? All right. No, it doesn't make sense. You're right. It doesn't make sense because this should be the easy stuff, right? This is not what is hard about optimizing code. You'll note that I don't have any loops up here. I haven't had to use any math to prove that it's safe to optimize this code. There's no alias analysis going on. Instead, there's merely tons and tons and tons of code in a place it doesn't belong. And that's kind of the fundamental problem that I keep running into with LLVM's optimizer. Tons of code in the place it doesn't belong. And that's what we really need to fix, all right? LLVM's optimizer does the math, the alias analysis, and all these other things really, really well. What it doesn't do is keep this junk out of your function, all right? Okay, so how do we fix this? Because at the very highest level, optimization is all about inlining. A lot of people don't realize how important inlining is. And so I'm gonna try and explain why inlining matters as much as it does. So in a normal optimization pipeline, you get to do very little interprocedural optimization, right? There are some things you get to do. LLVM has some very clever passes. I'm looking at you, Nick. Some very, very clever passes to do interprocedural optimization, but they're still incredibly limited. The best way we have to do interprocedural optimization is to inline one function into the other and then just optimize it there. Because that actually builds the control flow graph, the data flow, all of the things we need in LLVM to run the optimizer. And so inlining essentially forms pairwise interprocedural optimization at a much more general level than any of the specific interprocedural optimization passes. And that makes it the kind of cornerstone of simplifying across procedures. And in C++ and in other modern programming languages, the procedures are the primary means of abstraction and composition. And so they're everywhere. And they're not real procedures. They're notional procedures to build up abstraction boundaries that you must look across to actually optimize the program. That's why inlining is so important to me. So how can we fix this? So my first idea, I've tried a few times to fix this, by the way. So my first idea of how to fix this was, it doesn't show up very well here. So I'll try and explain the first idea of how to fix this. So when the inliner sees this routine, it sees pushback. There's one hint, there are a few hints that it has that it might be able to do better if it inlined it. And that's the fact that when the optimizer sees this call to pushback, it has a null vector. It knows what the finish pointer is. It knows what the end of storage pointer is. It knows the size, right? It can compute the max of the size in 1, That's all constant foldable. Okay. It knows what max size is, so it can constant fold that as well. Okay, so the length becomes a constant. We're doing pretty well here. So we can see the allocation. All right, LLVM actually has some tools that will hack on allocations. We can delete allocations if we want to, right? We're going to actually be able to see a lot of this. This move is going to vanish because we know that start and finish are equal to each other. And so we're going to be able to delete all of the move code, okay? This delete thing is going to go away because we know start is null, right? We're going to end up just setting a few member variables and doing the actual pushback. That's actually pretty good. We should absolutely inline this function. Unfortunately, we don't get to do any of the lovely things I just described. None of that happens in LLVM today. The reason is that LLVM doesn't see all of this information that is trivially available to it. Because what LLVM looks at is actually this top line. It looks at the signature, and it looks at the function arguments to the signature. And unfortunately, even at the LLVM layer, the function arguments here are a pointer to this pointer, and a pointer to the value you're pushing back. Neither of those is constant. Neither of those tells you anything. Instead, we have to look through this pointer to the values that have been stored into the object, and then look at the loads of those values inside this function to realize that, in fact, there are constants that we can propagate across the inlining boundary. So this essentially forms store-to-load forwarding across the inline boundary. Without this, every single C++ function which has this pointer and which is called with constants in the members of the object is being misoptimized by LLVM. That's a pretty common pattern, okay? So this is a really fundamental thing, right? Every single C++ routine that does that is getting misoptimized because LLVM thinks there are no constants when in fact there are. So that was my first idea of how to fix this. Unfortunately, this doesn't work, because it puts in yet another basic block boundary. Because how do we do store-to-load forwarding? We have to scan from the call site up to find a store, right? We have to scan from the start of the function down to find a load, and we have to make sure that there's no other store, no other thing going on that could possibly clobber that stuff. And well, that means they have to be in the same basic blocks essentially, or the complexity goes off the deep end, we give up, and we don't do a very good job. And it turns out that it's never in the same basic block. I actually wrote a store-to-load forwarding pass. I mailed it out to the mailing list, and it's completely useless because the IR that actually comes out of it, the C++ front end and any other front end, is going to have basic blocks around your call rather than around the stores of constants. And it turns out, you know why that's the case? Well, because the LLVM optimizer was like, hey, I can hoist that store of a constant up above the branch. That's fine. So the LLVM's optimizer itself is thwarting you at doing this. It makes it incredibly hard to actually accomplish store-to-load forwarding because of this basic block boundary. It's reminiscent of this basic block boundary we had in the selection DAG too. We'll come back to that. Okay, so new idea. Why are we inlining grow at all? We're inlining into a block of code which is algorithmically determined to be cold. That's why there's an allocation in it, right? We should never inline here. This is a terrible inlining decision in the first place. But how do we recognize that? How can we tell the inliner, right, that this code doesn't get executed very often? There's roughly one way we can do that today, and that's with the little built-in expect thing in the C code around the condition, and that built-in expect gets turned into branch metadata, and that branch metadata gets turned into a branch probability info, which we can then use to figure out that things are cold, except that all of that stems from an analysis pass. And we don't have analysis passes in the inliner. So the inliner can't tell that this is cold. It can't tell that there's this thing going on here that it should know about, and it can't avoid inlining into the code. And so this is why that other thing is near and dear to my heart. So where do we go from here? We need some path forward. So I'm going to outline a few things, and hopefully you guys are going to have lots of questions and maybe even some ideas, and oh my goodness, we could have patches too, but that may be asking a bit much, right? And I'd like to actually discuss the path forward because I think this is really, really important. Exactly what we do to address some of these surprising limitations of the LLVM optimizer. All right, First and foremost, we need to fix this inliner. All right, we need to fix this entire problem that I've just described. Both of the approaches I described should work. They're both important for different use cases. We need to support both of them in the optimizer, but we need a lot of infrastructure changes to get there. So the first thing we have to do is we have to break that basic block boundary limit. We need to build some very serious and clever infrastructure inside of LLVM that will allow us to quickly and easily look across trivial control flow edges and see that in fact there are obviously dominating stores that we can forward into loads. Once we have that, we need to go through the entire optimizer and find every place that we're doing store to load forwarding, there are like 4 of them at least, and teach all of them to use the same infrastructure, because this is not a problem unique to inlining. There are a lot of places where we get, clobbered by this basic block boundary and a very naive idea of trivial dominance. Then we need to go in and completely change how the pass manager works and teach the pass manager how to do much more robust management of a pass and its dependencies so that module passes and call graph passes can depend on function analysis passes in a sane and tractable manner. Today we have kind of a hack that allows module passes to do it, but it's computationally expensive. We don't get the caching behavior that we would expect from the LLVM pass manager. It's not an ideal solution, so we need to go in and really think about this and make sure we get a proper solution, a well-designed solution. Finally, we have to teach the inliner about profile information, and this is not a trivial undertaking. We need to spend a lot of care and thought about how we should inline based on probability of execution. All right, what is the right signal for the inliner to follow? Is it, inlining into hot blocks? Is it inlining into, normal blocks? Is it not inlining into cold blocks? What about loops? What about trip counts of loops? How do those factor in? What about the size of loops? We really need to think about how to make the inliner much more profile and execution aware instead of just instruction size aware. Today, it's just thinking about instruction sizes, and that's not enough to make the correct decisions. Finally, we need to do something at a very fundamental level to hoist all of this useless code that ends up in our functions, but is told by the developer, right? Often by the algorithm itself, that it's cold, that it's not the hot path. We need a way to handle this. Because the worst case, well, not the worst case, a very bad result of doing the first couple of things here, right, is that we're going to go and inline very carefully and cleverly, and if you separate all of your code into lots of different functions, then we'll do the right thing and we'll actually prioritize the hot path and not the cold path. We won't bloat the code in the cold path. But we can undo all of that if the user, for whatever reason, happens to just write their functions sliced at a different granularity, right? If the user chooses to pick different boundaries for the functions, then inlining correctly won't help. We need the ability to actually split a cold region of code out into its own function. We need the ability to manage the calls to that code very carefully and actually minimize space. And this is something that will have a really profound impact with the way LLVM's inliner and the way LLVM's optimizer is structured. Finally, we need to move completely away from basic block limitations. I'm actually really excited about the work to move away from the selection tag, because it has some hope of giving us a scalable, fast way of doing high-quality instruction selection across basic block boundaries. I think that's going to be very powerful. I have a fairly controversial, well, I thought it would be fairly controversial. Several people have agreed with me that I didn't expect to. Idea that we need to move away from the select instruction entirely. I think that select was a mistake. And I used to think the opposite, and I've finally come around to this position. I think that we actually already have the proper representation in the IR for a predicated value, and that is an empty control flow graph with a phi node to predicate a value. And I think that we should write analysis tools and C++ APIs to allow developers to actually think in terms of empty control flow graphs and phi nodes the way they think in terms of select instructions today. Because phi nodes are much more flexible, they're much more general, and you'll actually get a lot more powerful. The canonical example is that today you can have a binary select instruction between 2 values, but you can't do a switch between in values. And if we actually canonicalize on the phi node, then we get that for free, because we've already generalized the control flow of the IR very effectively. We've got to rework the pass structure for LTO. It's just a disaster, okay? And this is something that is actually very easy in principle to do and very hard to actually do the scientific work to say, yes, this is the correct pass structure and not this other thing. We need to do this systematically. We need to actually measure everything and get a very, very strong LTO pass management structure. The biggest difference is that the link time passes are going to be a different sequence of passes, a very fundamentally different sequence of passes from the module optimization passes we run in each compilation. And that's going to be a pretty significant shift for LLVM to go through, and there are a lot of hard trade-off questions we have to ask there. Finally, a couple of things, and at this point I'm into kind of pie in the sky. I don't have any thoughts of how to do some of these things, but I think these are other really interesting things for us to look at in the next couple of years. I would love to see the vectorizer productionized in a slightly different way from what a lot of people think about when they think about an auto-vectorizer. I would like an auto-vectorizer which never makes code slower. All right? And that is a very, very high bar, okay? This is incredibly challenging, and I think it's something we should actually step up to. We have now one of the most powerful auto-vectorizers I've seen in a compiler. I'm really excited by what it can do. And I want to try and find the heuristics that allow us to turn it on all the time, everywhere, and get really efficient and reasonably sized code anyways. I think we actually need to go and complete our loop optimizer. I think it's been one of the kind of long-standing missing pieces. I know that I've got some ardent supporters here, Toby. I hear you, right? We need to actually build real loop transformations into LLVM. We need to be able to do a loop fusion and loop splicing and every buzzword loop optimization in the world. A lot of people don't understand why I like this. I don't have any loops that will actually benefit from it. That's not what I'm after. I'm not after performance here. I never want to get into an argument with a developer about why they've written their handcrafted, incredibly complex and hard to maintain loop just so that it executes just right. That's a terrible trade-off. That's a terrible engineering trade-off, right? The whole point of the optimizer is to let developers write the obvious, semantically clear code they meant to write, and to let the optimizer lay out that code in a very efficient way. And until we actually have a really aggressive, really powerful loop transformation suite, it's going to be hard to actually win those arguments and get people to write the simple, clear code that they should be able to write in the language and still get the performance they expect and need. Finally, we do need profile-guided optimization. It's this huge, glaring, missing feature in LLVM, but fortunately there's a whole lightning talk about that, which I'm going to shamelessly plug here. And you should go to that, and we should really talk a lot about how to get profile-guided optimization into LLVM. It's going to be very, very impactful. And so, with that, questions? 5 minutes early.
Questions?
No questions?
Or did you stun everyone into silence?
So you explained what LLVM is doing for this code, but how does GCC perform?
How does GCC perform in what way?
On your example with the
Oh, on my example. GCC inlines the daylights out of my example. This allows it to optimize it fairly well. It also means that the code size is very bad. And as I mentioned kind of in passing, LLVM is generating significantly smaller binaries at O2 than GCC is. I don't know how much of that is due to this particular pattern, of course. I haven't really looked in depth. I do know that this particular pattern, GCC simply inlines all of it. And so it will actually get all of the information it needs to delete the code.
So thank you for this interesting talk. It looks to me that you try to work hard to optimize some code at a very low level. But if you think at the higher level, for example, in the statics analyzer, you have mostly all this kind of information you need. And that's something we are trying to work right now, is just to extract from the static analyzer the information, such as, for example, if you look at the side effect, if you are able to represent, to abstract the side effect of your vector your STD vector stuff, indeed, you can realize that there is no useful side effects at this higher level, and so you can prune this code by using classical use-def elimination at that level. So maybe it would be easier to solve some of these issues at the Clang level, because you have most of this information there. So, but it's interesting to compare the different approaches.
No, I will happily. I want to discuss that because this is a really interesting point. There's a. You're not the first to mention this. There's a strong feeling by many people that we're missing out on these very high-level optimizations. I don't entirely disagree. All right. First off, we are clearly missing out on very high-level language-based, semantic-based optimizations. I have a couple of points though. One, I think it's a mistake to pursue high-level optimizations until the low-level optimizations which are relevant to them are as good as we can make them. Okay? Now, the difference between as we can make them and as good as they can be is the difference between the ugly slide I posted and the bad slide I posted. Okay? The ugly slide were things that we need to fix. We know how to fix them. They're right in front of us. We have to go and fix them. It's a mistake for us to focus on higher level optimizations which overlap with those until they're fixed, because if we do, we'll draw the wrong conclusions, we'll measure the wrong things, we'll think we've accomplished more than we may have. Does that make sense? But there's another thing as well. I gave stood vector. That was my example. I mostly gave that the problem of giving a presentation. I gave a contrived example so I could explain it in 20 minutes, and you could follow along with what was happening. The contrived example I gave is not the example I care about at all. It turns out that lots of people implement stood vector. Now, I don't think they should. I think we have a library for that. But reality, if you go out and look in the world, you're going to find hundreds and hundreds of implementations of stood vector or an analogous data structure. LLVM has 4. Okay? So like we're not even immune to this problem ourselves. So given that, I think it's really important to come up with an optimization strategy which can optimize anyone's vector, not just stood vector. And that means that we have to have a really generalized view of things. And that can be very, very challenging to arrive at in the static analyzer. And everything I've seen is that LLVM is a better platform for decomposing all of these different source representations of stood vector, all these different kind of ways of typing in the code and structuring the functions into the same kind of canonical patterns of instructions that we can optimize with a single optimizer. And I think that's very, very powerful. I think it's going to be incredibly hard to come up with the same level of generality and broad applicability when we're working at a higher level, because you kind of necessarily have more noise in your channel, right?
There's also that not everyone that uses LLVM uses Clang as well.
There's that as well.
Not everyone programs in C or C++. So it's, you can't just think that if you're optimizing Clang, everything will be fine, because all the other people will miss it out.
To be fair, everyone I've seen really strongly propose this. They've actually done it in a very front-end neutral way, where the front end simply annotates the IR with annotations that give you the semantic contract that you can optimize under, and the optimizations remain general purpose. Any other front end can produce the same annotations, but it does put a burden on each front end to produce these high-level annotations to hide essentially a weakness in the low-level optimizer. And that goes back to my first point, right? We have to have a very strong low-level optimizer in order to build a strong high-level optimizer, or we'll build the wrong high-level optimizer.
So you are mentioning the size of the IR that is produced. Are you proposing to get an IR at a higher level in the optimizer?
No, I think that we just have bugs.
I disagree.
Jump up and down, Diego.
I don't think the size of the IR should matter. It's whether you can figure things out. So one question I had, but this is probably my ignorance, is why do stores and loads give you trouble?
Why do stores and loads
aren't they
give you
linked? Can they be propagated and coalesced? And
it's a store in one function and a load in a function in another function.
yes.
The challenge is precisely propagating it.
I'll ask you offline because I think this is things I'm not understanding about.
Okay. I mean, there's a whole lot of theory about how to do that, right? But part of the problem is that the inliner doesn't get to use any of the analysis passes which actually build up the interprocedural analysis which says how you can propagate a value from caller to the callee.
Yeah, I think you answered the question.
Yeah. Other questions? I think we still have a little bit of time.
So I think you said that the link time optimizer needs a fundamentally different set of passes compared to
A different sequence of passes.
or a different sequence. Could you explain a little bit more why that's needed?
Sure. Okay. What happens today? You run the compiler. You run compiler at 02, whatever, right? It's going to go through. It's going to run the standard set of passes. One of those passes is the inliner. Another one of those passes is the vectorizer. There are a few others. I'm going to call these passes informally information destroying passes. These are passes which fundamentally are going to remove information about the program that used to be there. The inliner doesn't always do this. It's a little bit tricky to analyze. The inliner does this half of the time. The other half of the time, it's actually preserving information. The time that it's destroying information is very particular. When it looks at your module and it concludes that it's analyzing a function at the API surface of the module, and therefore it won't be able to inline that function into its callers, it decides to use different heuristics for inlining. Well, that makes perfect sense if you're compiling normally. But then when you go to the link time optimizer, you have inlined these functions under the assumption that you would be unable to inline one step further. And then you've removed that assumption. So that's the most fundamental example I have. The vectorizer is another good example. If you run the vectorizer on your code in your first pass, then in the second pass, the inliner is going to look across modules, but it's going to see code which has been vectorized. That code may be dead. It may not actually matter at all, but we may not be able to understand it because the loop is now significantly more complex than it was before. Right? We've actually lost some ability to analyze things easily. Now, a lot of these things are things we could compensate for with compile time, right? With enough machinery, we can undo the work of the vectorizer potentially, but that is the exact opposite of what we want in a link time optimizer, where we're actually really, really gated on compile time all of a sudden. And so it's not really a good trade-off. What we really need is in the early stages, right? What we want to do is we want to do a series of optimizations which do not destroy information, and which minimize the amount of code that comes out. We essentially want to shrink without destroying information. Then we ship that out without doing anything else to it, right? Then in the link time phase, what we want to do is we want to do a couple of things first. We want to optimize globals a lot earlier and a lot harder, because the link time optimizer is actually going to just delete huge swaths of code if we do that, and then it won't spend a whole lot of time inlining and optimizing that code. And that's the whole point of the link time optimizer. And we're kind of, we get it, but we get it at the very last stage when we've already paid all the cost. Then we want to go through the standard inlining pipeline that we have today, essentially, and the standard optimization pipeline. I actually think that the optimization pipeline at link time will look very much like the optimization pipeline we have today all the time, with some additional passes at the very beginning that take advantage of the fact that certain invariants are met coming in. For example, we don't need to form SSA coming into the link time optimizer. It's already an SSA form. We can cheat egregiously there and get a lot of win for that. We really don't need to run inst combine and simplify CFG 3 times before deleting globals, right? So there's several small changes, but those are pretty small. The big change is in the per translation unit optimization to preserve the information.
So you said the scalability problems with LTO are basically fixed. The last time we tried running it on the FreeBSD kernel, it took 64 gigs of RAM, it ran on a single core, and it produced a kernel that didn't boot.
Yeah, no. I should be a little bit more clear there. One of the scalability problems that we knew about that didn't involve debug information was fixed. Specifically, linking of types used to be quadratic and now isn't, because we don't link them. It's a bit of a hack, but okay. Debug information is still really kind of messed up. So there are plenty more scalability problems to attack.
So do you have any views on how we can take advantage of parallelism when doing link time optimization? Because this is one of the things that we immediately lose when we chuck all the modules together and then say, now in a single thread on this 32-core machine, let's do all this optimization.
Yeah, we should parallelize the pass manager. And it's probably going to be one of the most invasive changes to LLVM's architecture that's ever been done. But I think we should probably do it in the next year. I can keep talking about that for a whole another hour, though, so we should probably... More questions? More questions? I haven't even finished my caffeine. You're not going to yell at me anymore, Diego? Oh, we've got more. We've got more.
Yes, but no.
Just a small one, more or less. You mentioned that you think that all relevant optimizations paths are already in LLVM. So I looked at it and looked for analysis that tells me what's the range of values that a variable can be. And I found it can only tell me that's a constant. I looked at in Clang, actually the static analyzer in Clang has this analysis. Why isn't there such thing in LLVM?
So there are at least 2 people in the room, maybe 3, who can answer this better than I can. One of them's laughing right now. So value range propagation is kind of a big theoretical optimization. We used to have a pass in LLVM that did it. If you go into version control history, you can still find it. It probably wouldn't take too much to reconstruct it. I even kind of know the guy who wrote pieces of it. He's over here trying to hide. Here's the kicker. It turns out that pass didn't help any code. That's all it is. It didn't. It slowed down the compiler. It didn't make programs faster. It didn't even delete a lot of code. It's primarily useful for static analysis. And there weren't even a lot of static analysis engines using it in LLVM, and so we got rid of it. There's no mystery here. It's very, very easy to write in LLVM. The other thing I will clarify, what I was saying was that I don't have specific problems with the set of passes LLVM has for LTO. I'm not trying to say we have all of the passes we will ever need for all time. That's pretty clearly not true. But VRP in particular is just not a useful pass for an optimizer based on our experience thus far.
Simplified demanded bits gets a lot of it.
Yeah. We have another question?
So when I looked at the value range stuff, it says you can have the minimum here and the maximum here, but a pattern that I see a lot in code is this integer is actually a bit field, and up here we set this bit, and then down here we branch on whether that bit is set or not. There's no way that I could see of getting that information, and we don't even have that in the metadata that we define for specifying ranges.
Simplified demanded bits does catch that case. When it's self-evident in the actual code what's happening. I don't know that there's anything in the metadata that allows it to cheat from front-end semantics. But also the bit field code generation changed pretty radically, and I'd be interested if that's still as problematic as it used to be. We used to recombine pieces of bit fields from different loaded values into a new value, which made the simplified demanded bits problem significantly harder, and it gave up more often. And now we don't do that. We load a big value and we just extract the bits we need. And the particular algorithm for simplified demanded bits finds that easier to analyze, and so it skips fewer cases. So it might have gotten a little bit better, but that's an incremental improvement. I don't know. Wait. He's bringing you a microphone. Wait for your 15 minutes of fame, Diego. Come on.
Last question, because after the other talk is starting.
No, it wasn't related to that question. I don't know if LLVM as a scalarizer, GCC catches those cases with scalarizing. It scalarizes the bit accesses.
We also do that.
Okay. But you mentioned something different.
Okay.
That was my confusion.
When we can, we will completely scalarize the bit field. The only time you don't see that is when we can't turn it into a scalar. All right, well, thank you all very much.